So let's start. So it's very nice and appropriate that we will start today with the Klein-Gordon theory. As we discussed yesterday, when you consider the complex version, that's the basic setup in order to study the theory that describes the Higgs boson or the Higgs sector in the Standard Model. And today, Engler and Higgs were informed that they are the winners of the Nobel Prize in Physics. So we're very happy for them. But that theory was written down, or at least they laid down the foundation so that the Higgs sector of the Standard Model could be written down. And this is something that happened 50 years ago. So we have a lot of ground to cover. And so we better get going. So this is a theory you studied today in the tutorial. Okay? So the field equations are given by this. So sometimes people like to call this operator a box. So you will see a box, but there is nothing special about that. One trick to solve any differential equation of this form is to write the Fourier representation. And we will only transform the space components. So you did all this in the tutorial today. There are several conventions for the Fourier transform. Some of them have a factor here, some of them don't. But in the end, well, they are just conventions. So I encourage you to go through perhaps one more convention where there is no factor here. Okay? So we have this.
Freddy, should I think you have phi squared in the equation?
Oh, sorry. Yeah, there is no phi squared. Yeah, that would be a little bit more complicated. We will have a phi square, but that will happen later. Not now. Okay. So we have k dot x and our field t of k. When you plug this into this equation, the equation becomes an equation of the form second derivative in time of our field phi tilde. And then we have, so we will get a minus sign from the metric, and we will get a minus sign from the I square, and that gives us something that looks like this. And this looks like an equation for a simple harmonic oscillator with frequency square given by this, so we can call it WK squared. The solutions so we can write down the solutions. We'll have two solutions. Okay. Let me see my conventions. Well, at this point, let me call this one A of k and this one B of k. Okay. Now the field phi was real. Was a real field. Okay? That means, as we discussed yesterday, that this must be true, okay, in order to ensure that the field is real. And therefore, we conclude that B of k must be equal to A of minus k conjugate. So that plugging this back into the expression for the field phi, we find that the most general solution for our field is integral d3k over 2 pi 3/2, and then we can start with ak e to the minus I omega kt plus I k dot x plus a minus k conjugate e to the I wkt plus I k dot x. Now, when you look at this equation, when you look at this expression, the expression is begging you to do something. What is it begging you to do? Well, we know that the theory is a relativistic theory, so this actually looks like the norm of a 4-vector, okay, or the inner product of two 4 vectors. Well, what are the natural 4 vectors? Well, we have t and x that we usually denote as x mu. So it seems natural to also define w, k, and k as a 4-vector. And then this object over here looks like minus I k dot x. So that looks pretty good, except that here things don't quite work out. Okay? So any suggestions? Yeah. So on this, throw it away. Well, there is a less radical solution, which is just take this. After all, k is just a dummy index, right? Because it's an integration variable. So we can just take this integral here and change k by minus k, okay, at the level of the integral. Here we don't pick any change in the integral, right? Because these integrals are from minus infinity to infinity, so we don't pick any signs or anything. So we just change k by minus k, and we're going to get, so here, change variables from k into minus k. And then we find a nice formula for our field. Okay, which is given by this. Okay, that looks pretty good. Now it turns out that it's convenient to redefine these A's and introduce some normalization. Okay, so we're going to define this. This is just this is for convenience. Okay. So this is just because we know what we want to get in the end. I mean, we can carry out the computations like this, and then in the end realize that it would have been more convenient to define a function of k given by this formula. So we will just do it and put the normalization here in front and replace the a's by the little a's. Okay. In the tutorial, you were also asked to compute the Hamiltonian of the theory. In this case, the conjugate momentum to phi is nothing but phi dot. And when we compute the Hamiltonian, I'm sure you all found that you get an integral over d3x of pi squared plus this term squared plus m squared phi squared. And there is probably a half in front. So this is very good. We have positive terms. If we assume that m is real, we have all positive terms. So this is the analog of the rest mass energy of the field. This is the analog of the kinetic term in classical mechanics. And this is something slightly new. This is basically the energy that you have from shearing the field. Okay? So there are three terms that contribute to the energy of the field. But this is precisely the reason we decided to study this theory and not just go ahead with electromagnetism. The reason is that we have our nice canonical momentum conjugate to phi, and we can now proceed as in quantum mechanics, okay? But before we do it for this, let's actually quickly review what we do in quantum mechanics. Or how we got it from our classical description that we had yesterday, where we had some variables, some coordinates, and in the Hamiltonian version, we had the momenta. Okay? So what do we do to go to the quantum theory? We promote these classical variables. We promote them into becoming operators. And we usually think about the Schrödinger representation. Or in the Schrödinger picture. This is the one that we learn first, in which the operators are just entities that don't depend on time, and only the wave functions depend on time. Okay? But it turns out that in quantum field theory, it's more useful, or at least in the canonical version that we're going to do, to think about the Heisenberg picture. So what's the difference in the Heisenberg picture? That's right. Here, states don't depend on time, but operators depend on time. And how do you get operators to depend on time? Well, the time evolution is given by, if you have an operator, you can think about this operator as given at some time 0, and then you induce the time dependence by acting on it with the Hamiltonian of the theory. Okay? So in the Schrödinger picture, we usually think about imposing canonical commutation relations of this form. Okay? And yes.
So you're assuming that your Hamiltonian is time independent, and
Yes.
I guess that we're going to use this Hamiltonian over here
Yes.
somewhere. How do I see that this is time independent? In principle, it's not, right?
Well, we will hope for the best again and see what happens. But that's a good question, yes. So this Hamiltonian is time independent, and hopefully something like that will happen. Otherwise, we will be in trouble. Okay. Now, this is the time, again, to remind you that we are setting h bar to 1. Okay? So we're working in units where the speed of light and h bar are equal to 1. Now, this is in the Schrödinger picture, but you see that nothing happens, or I can promote these commutation relations into the Heisenberg picture if I do something. If I take each of these operators are operators after all, and I evolve them in time, I can promote them into commutation relations in the Heisenberg picture as long as I think about this operator and the next one evaluated at the same value of time. Okay? So I can promote this into commutators which are called, for obvious reasons, equal time commutation relations. Okay. Now, once again, the labels A and B are just labels, okay, that describe different configurations or different possibilities for our coordinates. In our case, the labels are replaced by the position in space. So if we have this formula for the quantization in classical mechanics of a classical mechanical system, it's only natural to propose the same class of commutation relations when we promote phi to become an operator. Okay? Yes?
So the commutators vanish if you put them at different times, or are we not saying that they're
We're not saying anything what happens. We will see what happens at different times, but not at this time.
Okay, right now.
It will be at some time in the very near future, but not now. Any questions?
So we're imposing this condition.
Just like we did here.
Is there any problem with referring to Ilya's question if I take this to, instead of being delta 3, delta 4 of x minus y as 4 vectors?
Very soon we will decide what happens at different times. Okay? But for now, I take this as the definition of the theory. So we're going to describe a theory that depends on operators, and the operators satisfy these commutation relations. Okay? Very good. So, yes, you're laughing, right? Yes. Yeah, the stapler didn't do much this time. I think that's partly my fault. So, well, let's fix it now. Okay, so just like when you have harmonic oscillators, these momentum modes will also become operators, okay? So by analogy, we will be hoping that these also become creation and annihilation operators. Now, the complex conjugate of this classical object should become the adjoint of this operator, okay? In order for this operator to be real, now the condition for this operator to be real is that this mode becomes the adjoint of this operator. How about the canonical conjugate operator? Well, we just have to take the derivative with respect to time. And what do we get? Well, remember that here, time enters as minus I wk times t. And here we will get it with plus sign. So we just get minus I wk ak e to the minus I k dot. Sorry, these are 4 vectors. And on this side, we get plus I wk a dagger Note that I did something important here. I assume that these operators are time independent. Okay? That's why in the derivative, they were not affected. Okay? So in the end, I'll ask you a question referred to that. But for the time being, it's obvious from my construction that these operators only depend on k, and they are not time independent, and they are not time dependent. Okay. Very good. Yes.
So when we quantize the field, we treat k and x as parameters, as opposed to like if you're doing old quantum mechanics, you treat x and p as operators. Is it obvious?
Sorry, what am I treating as?
So k and x aren't operators, right? They're just numbers, and k dot x.
K and x. Yes, of course. The k, x is a parameter here.
Yeah, that's what
yes.
Yeah, is there?
Yes.
I mean, is there an obvious reason why they don't also become operators? I mean, because old quantum mechanics, p and x are operators. So.
Yes. Well, maybe in a tutorial, or we will try to derive the non-relativistic analog of what we are doing here. Okay. In the non-relativistic analog, you will see how the x operator and the y operator will emerge, and the p operator will emerge. Okay. But here, all we are doing is thinking that we are describing a classical system where the coordinates were parameters, and we are just following the same as we did. We are treating the classical system as a canonical system, and we are following the same rules that we had in this case. Yes?
So I got a little bit lost with the analogy that you're making with the harmonic oscillator. So you're saying that I want to quantize my field, so the only thing that I can quantize is just the A and the A of K, right?
Well, there is nothing else. There is nothing else that can be quantized in this format.
Then with the analogy of the harmonic oscillator, then I should expect that the commutation relations of A and A dagger resemble the ones that I have for the harmonic oscillator.
Well, now there is nothing. There is nothing else I can do. I already told you the rules, and everything has to follow from these rules. Okay. Okay. And now you should not assume anything.
So shouldn't it be equivalent that by making just analogy to the harmonic oscillator without referring to classical mechanics? Just assume that AK and A and A dagger behave as
creation and annihilation operators.
With their right commutation relations, and obtain these commutation relations for phi and phi.
Well, you could do that. However, the two things will be equivalent. But the way you got that in the first place in classical mechanics was by starting with these commutation relations and then deriving the existence of the creation and annihilation operators. Okay, so those commutation relations were a consequence of these commutation relations. No, in the quantization of the harmonic oscillator of the classical system. Yes.
I missed the reason. Why did you say you take x to be time independent? Just because they don't have the timetable, you just assume.
Why am I taking the a's to be time independent?
Yes.
Because they are time independent. Yes. Yeah, but
so I guess that fixes your commutations at different times as well, right? Because you can now compute them and you can. Well,
yeah. So now we're going to see what happens. Yes, that's true. Now we can take these fields. Once we figure out what the commutation relations for the a's are, then we can do commutation relations at any times. That's a very good observation. Yes.
So when
yes.
we solve the wave equation, we basically took a family of solutions in terms of plane waves, right? So
yes.
We could have taken a different basis of solutions, right?
Yes.
Would the same thing would have happened? So would I have like some coefficients depending only on space, and then we would have promoted them to operators and they would look the same, or is it very special that we just?
So you see here I haven't done anything, right? These commutation relations don't depend on the solution, right? So now I'm going to derive what these guys have to do after I have postulated these commutation relations. So if you had chosen any other way of representing your solution, then you would have to do exactly what I'm about to do. So the answer to your question is yes. Okay. So now by popular demand, okay, So you all want to know what the AKs and A daggers do, okay? So we could do that first, or we can consider the Hamiltonian first. Since I'm giving the lecture, I get to choose. so I get to choose to look at the Hamiltonian first. Okay, and the reason we want to look at the Hamiltonians is that eventually we want to understand the spectrum of our theory. And just for the harmonic oscillator, the same thing happened. You look at the Hamiltonian first, and diagonalizing the Hamiltonian is the way to find out what the spectrum of your theory is. Okay? So we have to consider our Hamiltonian that we have written there. And you will do this calculation in detail in the next tutorial. But for the time being, let me show you some of the terms, well, actually, schematic form of the terms that you get by simply plugging in the expressions of phi and pi into the Hamiltonian, okay? And we're going to see what the terms look like. So when you do, you're going to get an integral over d3x. Now you're going to get an integral d3k. I'm not going to write all the factors. The factors of 2 and pi are going to be your job, and the factors of maybe I. So we have 1 per field. The Hamiltonian is quadratic in the fields. So we're going to represent one of them as an integral over k, and the other one as an integral over k prime. So in the term where we have pi squared, the momentum square, we're going to represent the first one with k and the next one with k prime. Okay? And the same thing for all the rest. Now, we're going to collect terms according to the way the factors of the operators A and A dagger. So the first class of terms will be of the form A times A. Okay? What kind of things can I expect to get? So from the pi squared term, what do we get? Well, we get 2 factors of WK, right? So I'm going to leave the exponential at the end. Okay. What else do we get? Now, we can also get a contribution coming from the gradient of phi squared, right? Which will contribute to the A term. So from the gradient of phi, we're going to get something that has the inner product of k and k prime. And of course, we're going to get a contribution from the phi squared term, and that contribution will be m squared. Okay? So the next one in the list would be A of k and A dagger of k. And this one comes with this factor, exactly from the same kind of terms, but with an interesting change in signs. Okay, this is a plus. This is the next term. Now the next term is something that looks like A of k dagger A of k prime plus last one. All right. Okay, so that's your Hamiltonian. Of course, we can simplify this, right? Yeah, integrate over x. That would be a great idea. So let's integrate over x. So the integral over x, we're going to have an integral of the form e to the, for the first term, it's going to be an integral of the form that is a delta function of this form, right? And that would be for terms, let's give names. So this is term 1, 2, 3, and 4. So the terms 1 and, thank you, we'll have this delta function. How about the terms 2 and 3? They will have delta function of the form k minus k prime, okay? Because there is a minus sign. That seems like a very trivial change or difference between these terms, but it has a profound impact. And the reason is the following. Well, let's look at these ones first. If this is true, okay, if k is equal to minus k prime, this then becomes plus k squared, and this becomes wk squared. And what do we get? 0. So this cancels out. So this is 0. And the same thing happens for this guy. Exactly for the same reason. Now, in this case, once again, we get k squared, but now with a plus sign, right? Because they are supposed to be equal. And here we do 2. This also becomes wk squared, and therefore these terms become proportional, or 2 times wk squared. And the same thing happens for this, okay? Now there is something fascinating. So you were asking about the time dependence of the Hamiltonian, right? Now look at these terms. In these terms, well, yeah, those actually were canceled out. But before, if we had not done this, okay, note that the time dependence of these guys is there, right? We will have W2 or WK plus WK prime times T. So we have become 2 times this. So it's quite remarkable that precisely that cancel out, okay? So that's very convenient. And this one too. Now, how about in these cases? The time dependence actually cancels. What a save. So we get that the Hamiltonian is time independent, as it should have been. And it becomes an integral d3k. So I want you, so part of your exercise during the tutorial is going to be to figure out all the factors of 2. But in the end, you should be able to show that this becomes this one, okay? After all the dust settles, you should get that.
In the third term, is that a minus with the E? No, over here. Right.
In number 3?
Number 3, is that a minus with the I? Next to the I in the exponential or not?
Here?
The last one.
Well,
But then the last one should be, I mean, there's some symmetry gradient.
Because it doesn't matter.
I is the first
I
one.
mean, the delta appears anyways. So the last term should be e to the minus I.
And the first one is minus, or the fourth one?
I think this is correct.
Yeah, but the
2 and 3 are fine, 1 and 4.
1 and 4.
There's a minus, right?
There could be, but that one is 0. Yes.
there is a plus or minus.
So that's no problem, okay?
Freddy, a question. Why is it so problematic if the Hamiltonian depends on time? So why would be?
Well, it's just simply that if we have really an inconvenience, because then our exactly the same structure that we have wouldn't have worked. Okay, the same structure that we have for the dependence of the operators would be different. Okay, if we're having an inconvenience. Yes.
Also, like a closed system should have its Hamiltonian time independent.
Well, that too, but since we don't know what we're doing in principle, we're just trying to find out whether this system that we got from this weird exercise makes any sense. It's actually a good indication that we are on the right track. Okay, very good. So now, in order to proceed further, we really need to know the commutation relations for A and A dagger. Okay? So once again, yes. Sorry? Yes, thank you. So the first step would be to take the relations, the formulas we have over there, which I don't know why they keep going up. They don't want to be erased, which is good because they are important. So we just want to take these two formulas and invert them in order to find AK and A dagger K in terms of phi and pi. Okay? That's also a simple exercise, which is a nice tutorial exercise again. And this time I'm going to write it in more detail. Okay. So having done that, we can now start and ask what the commutation relations are. Okay. So let's try. Let's actually do it here. So let's start by computing the commutation relation of A of K and A of K prime. Okay? So it wasn't very smart, I have to say, to put the A's over there while having to use it here. But let's try it nevertheless. So what do we have? We have two integrals, right? So we now have integrals over x and x prime. So one for each. Of what? Well, we will have e to the I k dot x plus k prime dot x prime, and the commutator of phi dot of x minus I wk phi of x and phi of x prime minus I wk phi of x prime. Okay? Note something interesting. The first thing is that we only postulated the commutation relations at equal times. But the AKs do not depend on time. Okay, so even though our formulas look like they depend on time, like they had an explicit dependence on time, this object is time independent, so we can set the times to be equal. Okay, so we're setting x0, which is t, equals to t prime, which is x0 prime. Okay, so we can use our commutation relations and find out what we have. So what do we get? So from here, and this is k prime, so we get phi of x dot with phi of x. So this term, oops, not quite, right? This is a dot, so these two commute, and this one will give me a minus I wk. And then this with this will be minus I wk phi of x, phi dot of x prime. Okay? So this one will give me a delta 3 of x minus x prime, while this one will give me minus delta 3 of x minus x prime. Okay? Now, having done this, I can perform one of the x integrals. So doing one of the x integrals, I'll be left with an integral d3x. Say I do the x prime integral, and then I have e to the I x dot k plus k prime. Okay? Sorry? Is this out? Sorry?
You want the dagger, aka a dagger, or just?
No, I'm doing AK with AK.
So here you can use the commutators and they just differ by a sign. So
The first one should be a rate of prime.
Yes, the first, yeah, one of them is W omega k and the other one omega prime. So which one goes with which? This one goes with omega prime. Okay. Very good, very good. So if you're even getting the primes right, then it means you're paying attention. Yes, that's pretty good.
It's actually the other way around. The first one should be fine.
Okay, very good. So Tibra is paying even more attention than you guys are. It's the other way around. However, this delta function is going to set the k's to be the negative of the other one, and therefore the omega k's will be the same. So we have a factor of I. From here we get wk prime, omega k prime, right, with a minus sign, so we get a minus sign, plus omega k times the rest of the factors. But on the support of this delta function, this is equal to 0. Okay? So we just learned from this little exercise that these two operators are indeed behaving as we expected. And the same calculation will show that these operators behave in the same way. Of course, your exercise will be to show what the next one is. So we're not going to do it here, but just following exactly the same calculations. You should get that the A and the A dagger satisfy these commutation relations. Okay? So now we're in business. Or that's what we think.
So when we might have these commutation relations, so T prime equals to T, is there anything to stop us choosing T not T prime? In which case would we not just get 0 for commutation?
No, we should get exactly the same, except that the commutation relations that we have postulated are at equal times, right? So later on, once we learn how to once we learn what these commutation relations are, we can go back and redo everything if you want at different times. But the AKs are time independent. So we can just work them out at any times we want, right? Get the answer. And then if you want at the end, you can go back and do it at any other times. In other words, we are going to do, at some point in the lecture, we're going to evaluate these commutation relations at any other time. Precisely using the fact that we were able to construct these ones, which are time independent. And then you can go back and check the whole consistency by putting any times there. You see the logic? The logic is, we only know this now. We construct the commutation relations for these operators, which are time independent, using the commutation relations we know. Once these guys are understood, we can go back and calculate phi with phi at any times.
I'm kind of jumping ahead, but
Yes.
I'm assuming that these are going to get you a delta t minus t prime.
We will see. No, they are not going to give you a delta of t prime. Yes.
So maybe this is just a notation, but it looks like the equation goes down for a dagger depends on time as well.
Yeah, that's a very, very good observation. And that's something that is going to be crucial to solve the riddle I'm going to give you at the end of the lecture. But by construction, they are time independent, right?
So the point is that these formulas hold for any time that you choose.
Yes, these formulas hold for any time that we choose. They are time independent, okay? Even though there is some explicit time dependence. So you see, I keep saying something that you're going to use at some point, you should use it. Oh. Do we have more chalk? Thanks. Okay. Okay. Okay, so we're about to face a more difficult technical problem than just the blackboards, but just slightly more difficult, which is the following. We're going to see, and we're going to do exactly the same thing that we do when we consider harmonic oscillators. So I'm hoping everybody remembers these formulas, right? And the explicit time dependence they have. Now we're going to take this Hamiltonian and do exactly the same thing that we do for the harmonic oscillator, which is to write the Hamiltonian in such a way that all A's are to the right and all A daggers are to the left, okay? We can do that very easily by simply using the commutation relation for this pair of operators, right? So how do we do it? Well, we can just write this as A dagger K, AK, up to the commutator. Okay, so that looks very nice. We haven't done anything special. This is what we do in quantum mechanics all the time, except that this quantity looks a little bit strange. So we have K and K. Yes, if you are surprised, you should be. If you're not surprised, you should be surprised. So we get a very nice formula here. The factor of 2 drops out. That's all very pretty. And then we get factor of halves, which is very important. And this guy gives us a delta at 0.
So it seems like you could have written down this same Hamiltonian totally classically in terms of these like mode amplitudes and stuff, these AKs, and in which case, you know, you would have just had a 2 times, you know, A star AK. And
Yes.
then if you quantize at that point, then you wouldn't have any.
Yes, but we know from quantum mechanics, right, that precisely this is somehow the canonical way to get. Of course, there is an operator ambiguity, is what you're saying. From classical mechanics to quantum mechanics, there could be operator ambiguities. And you could say, why didn't you just define the Hamiltonian, the classical one, to be 2 times this and not bother about this? Well, the answer is that when you quantize a harmonic oscillator and you do tabletop experiments, it's very important to get that the energy of the vacuum is not 0, right? And that precisely comes from the fact that this is the canonical object that you get by going from the classical mechanical system to the quantum mechanical system. You fix the commutation relation, you use the commutation relation, and you get the energy of the vacuum. Now, what we are finding is that the energy of the vacuum of our system just happens to be infinite.
So but writing it this way is just because you want to do an analogy to particle mechanics.
That's right.
Okay.
So, well, which is basically the only guiding principle we have at the moment, right? So we look at this and say, well, it seems we have a problem, but this is a delta function evaluated at 0 in momentum space, okay? So this was the starting point of this, was this, when we evaluate the 2 at the same value, but this has a representation in terms of an integral over space okay? So what we're finding here is that this delta function is nothing but, evaluating this at 0, give us 0 here, is an integral over all space. So this delta function is nothing but the integral over all our space, which is nothing but the volume of our space, okay? Sure, it's infinite, but it's just a volume. So we could say maybe that this is a physical answer. It's not completely unreasonable, because after all, it's just telling us that the space we're considering is non-compact, so there is an infinite volume. Okay. So what's next? So I see that nobody's leaving the room upset and disappointed by that infinity. Yes?
So the
Yes.
definition of that is an integral over omega k. Is that infinite as well?
Well, before we do anything, we have to keep going a little more. Okay? Oh, you had a question, yes.
What about if I use the commutation relation in these middle steps, right, where I have k and k prime different? Should I get the same problem of having this divergence?
Yes, in the end, you will have the same problem, because there will be a delta function that fixes k and k prime. Okay.
What about the integral over k?
Yeah, so we already have one infinity, so why worry about more infinities?
Well, because one infinity is the volume, the other infinity is, I don't really know what. I mean, because you explained one infinity by saying if we had a compact space, it wouldn't be an issue.
Well,
If
but
we had a compact space, we would still get an infinite momentum space.
that's right, yes, indeed. But before we move on, I mean, before we worry about that infinity, let's actually think about the Hilbert space of our theory. Okay, so the first thing, we're going to go back to this for a second, but before we discuss this, but the first thing is that, of course, we can define a state which is a vacuum, and it's only natural to define it as a state that is annihilated by all the annihilation operators. So we declare these to be annihilation operators and define the vacuum as a state that is annihilated by all these. So if we do so, we can now compute the energy of the vacuum, or the vacuum energy. By simply taking our Hamiltonian and act on the vacuum. Once we do, of course, the only thing that we get is the nasty term, which is 1/2, that's very important, times. So this seems to be our vacuum energy, or the energy of the vacuum. Okay? Now, many of you have suggested already that, well, maybe, well, that if we were dealing with a compact space, then this would be finite. But another way of saying is that, say we don't know the space is compact or not, well, we could only care, perhaps, about the energy density, which is the energy per unit volume. Okay? So let's think about energy density. And what is the energy density in this case? Well, it's just 1/2 integral d3k omega k. So this is great. We just got rid of that infinity by defining the energy per unit volume. So that's a more physical quantity to worry about, because if the space is compact, then we don't have to think anymore. Okay? However, life is not as simple, because we still have to do this integral. And this integral is an integral from 0 to infinity of the norm of k. So let me call it just k. So here I'm going to call, or maybe I can change it like this. Okay. Okay. So we have times some 4 pi, which is the angular dependence. And this thing depends on this little k, like this. Okay? Well, sad news. This integral is also divergent. So we also get infinity. So what you do, what is the first thing that you do whenever you see an infinity like this? You say, how can I get something that is finite? Sorry? Yeah, take a cutoff. Okay. You say, well, the bad limit is not actually the limit from 0. It's actually the limit for very high k. So I'm going to put something that is called a cutoff. Okay. So now I can see how bad the divergence is. We knew it was infinity, but let's see how bad it is. So it is, to compute how bad the divergence is, we don't care about the mass, because the problem happens for very high momentum. So for very high momentum, this dominates, and this is subleading. So I can forget about this and think that my integral is an integral over d3k, sorry, k cubed dk. The cube comes from 2 powers from here and 1 from here up to the cutoff scale. And this integral is an integral that behaves like the cutoff to the 4th power. Okay? So it depends as the 4th power of the cutoff. Now, is this terrible? Well, it depends on your point of view. In this case, we're considering a free theory. So very high momentum, that's where the problem happens, right? For very high momentum, we think about something that has very high momentum as a way of exploring what happens at very short distances, right? So we could say that maybe the problem is that we don't understand what happens at very short distances. But this is a free theory. How hard can a free theory be, right? I mean, we're basically doing the theory that is just a bunch of harmonic oscillators. So Some people would say, no, but that's what happens. You don't know what happens at very short distances. Well, that would be the correct answer if you were dealing with a physical theory. If you're dealing with a physical theory, say the standard model, right? If the standard model has divergences, then you should see the divergences as a way of telling you that there might be some other physical degrees of freedom or something interesting happening at very short distances. But in this case, we just have a free theory, and this is in our happy universe where there is only a Klein-Gordon field, and we get this divergence, okay? Now, how can we deal with this guy? Well, the answer comes from a question you guys asked yesterday. What do you think we could do? Let's go back to the original Lagrangian. Was that Lagrangian uniquely defined? Is there a way to add something to that Lagrangian that doesn't change the field equations? We could add a constant. We could just add a constant term to that Lagrangian, okay? So after all, the Lagrangian was not the only thing that we see physically are the field equations. So if we add some constant to the Lagrangian, so we can solve the problem by adding a constant. Yes.
So, how will I find the cutoff? I mean, if I consider, for example, a chain of harmonic oscillators, I have a natural length scale that will give me a natural cutoff in momentum space. But in here, I don't have this, right?
Well, that constant would actually be infinite, period. It's an infinite constant, yes.
Would adding a constant to Lagrangian be somehow equivalent to saying that you only essentially care about energy differences, right? So if the energy of the vacuum is offset by that.
Exactly. That's exactly right. Okay, so we can add a constant, or we can say, of course, we only care about energy differences and therefore we can just declare this number, whatever it is, as our reference point and then measure from there. Yes?
I guess it's kind of what we're just doing, but so if you basically choose your zero of energy, why did you say earlier that we want a vacuum?
That's a very good question. So now you're saying that we're starting to contradict ourselves. Yeah, so we shouldn't really think about this. And what is an indication that we shouldn't think about this? Gravity. So gravity tells us that if we have any vacuum energy, the vacuum energy will enter here. So actually, I think, so I hope you won't get confused. Here I'm calling this lambda cutoff, okay? And this number here has a different name. This is called the CC, the cosmological constant. Almost. Okay, so whatever energy we have in the vacuum should contribute to this number.
How do we know that we simulate a free theory? What we really have is only one field. So how do we know that we're not just neglecting all other terms in Lagrangian, like phi cubed or phi to the fourth, like self-interaction?
So that would be another approach. You would say, well, let's not worry about this. Maybe by adding other fields in the theory, something will cure this problem, right?
Well, not other fields, just self-interactions in the same field.
Yes, sadly, it doesn't work. Actually, that will make the problem even worse. But you could say, well, maybe by adding other fields. It will turn out that if you add fermions, then life can get a little bit better. So fermions can actually cure part of this problem. In fact, if you tune very, very well what the fermions that you add, then you can actually get zero, okay? However, zero is not the right answer because we know from cosmological observations that this energy density is non-zero. But what are the units of energy density? Yes, thank you. What are the units of 1 over volume? Yeah, 1 over volume would be energy cubed, and then the energy would be another factor of energy. That's what I was asking, really. In our units of h bar equal to 1 and c equals 1, right? Length goes like 1 over energy. I mean, this is just to say that this thing, when I write it down, you shouldn't be surprised what I'm going to write down. I'm going to write down something that has an EV to the 4th and 10 to the minus 3, okay? So that seems to be what we observe, okay? In other words, we get 10 to the minus 12 EV to the 4th. Now, if you want to estimate, this is our experimental observation and the theoretical prediction, by just thinking about these lambdas coming from the cutoff to the 4th of the standard model, or at least to the point of where we understand the standard model. It turns out that we understand the standard model up to energies of, say, 10 to the 12th. So we seem to have a small discrepancy.
Only 60 over.
Yeah. So one possibility is to add a constant to the Lagrangian, some E0, or maybe let's call it some E counter term. Okay? But then here comes the problem. You have to choose that number that we add to the physical Lagrangian, to the actual standard model, so that it will cancel this contribution to 1 in 10 to the 60, basically. Okay? So that little problem is known as the cosmological constant problem. Yes?
Can you close it again? Sorry.
So the point is that the cutoff should be the place where you think your theory will break down. Something else will come and save you, right? So at the very least, it should be the places where you have tested your theory, the energies to which you have tested your theory. And the standard model, we could say, has been tested up to 10 to the 12 EEVs. So we can use that as a lower bound, right, for the cutoff. So we put it in there, and we find that it disagrees with experiments by that much.
Wait, 10 to the minus 12 is a higher energy than 10 to the 4th.
Sorry?
For theory of, I don't know, quantum gravity theory would be a higher, would be
No, but this is not an energy, right? This is energy density. It's EVs to the 4th, okay?
It appears that the problem of the divergence comes from the commutation relations. Like, what if I don't have these commutation relations and I take a different approach than this canonical quantization approach? Would I have the same problem? Or
Well,
I mean, if there's another way of doing this.
yeah, we should definitely, let's see. Maybe I shouldn't erase this.
I mean, the question is basically, if I say that I use the commutation relations,
yes,
and I see infinites in something that shouldn't have infinites, shouldn't like ring the bell and say like this theory is wrong.
that we're doing something wrong, right, from the beginning. The problem is that there are physical effects that depend on this vacuum energy, right? So when you change boundary conditions in a quantum field theory, we can now use all this structure to compute quantities that now depend on or are properties of quantum fields, say in some strange experiments, say with the electromagnetic field in some cavity, okay? So if you don't take into account the vacuum energy, you will get the wrong answer for something that is called the Casimir effect. So we know it must be there. So you have two problems. You could try to modify all this in order to get rid of this problem, but at the same time, you will also have to get correct the predictions that are confirmed experimentally for the existence of this vacuum energy. Okay?
Yes.
Yes.
You said that the vacuum energy has been measured, but didn't you say it's empty?
I said the vacuum energy has been measured when you put the field in some cavity. Okay? Yes.
A vacuum energy is like an overall scaling or a background. And if we're talking about energy differences, that's like the scaling that we use. And a cutoff is the limit to the understanding of our theory. It seems like we're comparing a cutoff to I mean, how can we compare a vacuum energy to a cutoff? That is apples and oranges. Apples and oranges.
No, remember, we got that cutoff by getting precisely the vacuum energy of our oscillators. That's how we got that cutoff, right? Don't forget from where we got that integral. We got it from here, which has the interpretation of the vacuum energy of these oscillators, which do something important when we put it on a cavity.
Okay.
So if you get rid of one, you have to get rid of then you're in trouble. Okay? So I don't think that we should try to solve the CC problem right now. at least no. This is all very good, and I encourage you to think about it and discuss among yourselves, and then when you come out with a very good, reasonable answer, you tell Tibra, and if Tibra still thinks that it's a good and reasonable answer, you come and tell me. And then we can be next year in the for the Nobel Prize.
Wait, what is it? 5 of us then who?
Clearly, I don't care, but clearly the lecturer has priority.
Otherwise it won't.
and then the fellow.
Exactly. So you came right and then it has to be one at a time.
Okay, so let's go on. And let's discuss the Hilbert space as we were trying. So the Hilbert space, so we have three particles. So why? We said we have our Hamiltonian, which is our integral d3k. Let's forget about the vacuum energy and just write our Hamiltonian here. And we say, well, this looks complicated. I mean, it's a continuous system. So let's put this system on a box of some length L, such that the momentum, the possible values of momenta are quantized, okay? So they are going to be quantized in a lattice of this form. And the Hamiltonian for this system will just be a sum over all those oscillators with a sum of momenta in the lattice, okay? Very good. So now these are just a collection of harmonic oscillators. Then we can define, now you will see why I'm doing this. And the reason is that in this theory, we know what to do. If we have at least a discrete set of harmonic oscillators, we can define a state which is a tensor product of all the vacua of each of the harmonic oscillators. And define that to be the vacuum of our theory. After all, each of the individual ones is annihilated by their corresponding annihilation operator. And that implies that the vacuum of the theory will be annihilated by any of them. Okay? Very good. And now we can keep going and say, well, what about the excitations of this? So the excitations, again, will be given by applying the creation operator on this vacuum. So we can say, well, this is the number 1 in this vacuum because we have 1 excitation. We can start to put many of them in that vacuum. So we can put nk of them and get a state that is a state with nk in the k vacuum. But now we can put many of them. Well, first of all, if we now act with this on the full vacuum of the theory, we get an excitation with only that oscillator excited, okay? So we're going to call that object, when acting on the full vacuum, we're going to call it K, okay? Yes?
How did you know what your dagger goes to the vacuum? You haven't really shown if you show that somehow when that goes to the H3 at that particle somehow.
Yeah, no, I haven't told you that they are. I haven't actually proven to you that they will be particles, but they are definitely creating states in our Hilbert space, right? So it's up to us. It's up to us to how to interpret them. And we will see that they have a reasonable explanation, a reasonable interpretation as particles, okay? And so far, they are just excitations, okay? So you're right. I shouldn't call them particles.
Just a typo. The Hamiltonian does not have a half.
Thank you, yes. We got rid of the half with a commutation relation. Okay, let's see how much. We should really, it's very strange that we don't have a clock here. So,
It's 5 o'clock.
Yeah, I can see, but it's annoying to go back and forth. Okay. Now, let's use that analogy and actually use it for our continuum theory, okay? For the full theory, we will again think about this as a basic excitation of the theory, okay? Now, those of you who were in quantum field theory 0 will remember that we started the whole course by postulating the existence of a Hilbert space and declaring that there were states classified by momentum. So these are almost the one particle states of QFT0. But there is an almost here. So they are not quite yet. So, but before we try to make the connection, let's consider a few more things. Well, if we have several of them, we could define an object or a state in the Hilbert space given by this, which, if these guys were to be interpreted as one particle states, this will be multi-particle states. But something interesting is that whatever they are, you see that they have to be, whatever this wave function is, has to be symmetric in the exchange of labels. Why is that? Because our field quantization told us that these A-dagger operators commute among themselves. So we just learned that when we quantize a scalar field, leads to a system that has both symmetry. Okay. How about the normalization of these states? So if we have k dot k prime, what do we get? Well, this is nothing but the vacuum with AK, A dagger K prime acting on the vacuum, and this thing gives us delta 3 of k minus k prime. We're assuming that the vacuum is normalized. According to this normalization, we can write down the completeness relation, at least for the one particle states. And here is where we're going to see the difference between what we did before and what we are doing here. So in the one particle sector, so now we have a big Hilbert space, which we can think about a huge matrix. And this matrix has blocks. So we're going to write down the identity in the block that corresponds to one particle states. Okay? So that identity, according to this, is given by this here. But does anybody remember the one particle completeness relation that we wrote down 3 weeks ago? Does it look like this? Well, of course, it's a very safe bet to say no, because otherwise I wouldn't be asking. So you can say very confidently, say, no, of course it doesn't look like this. No, but there is a deep reason why it doesn't look like this. You remember we struggled at that time to find something that had a nice property. What was the property? That it was invariant under what? Under Lorentz transformations, right? This doesn't quite look invariant under Lorentz transformations, right? So if this is to be the same object as the one that we had, which was actually nicer, right, than this, the object we had at the time, if you remember, was something of the form d for k, delta of k squared minus m squared. This is all beautifully Lorentz invariant. We had this, and we had our states. And if you remember, when I wrote down the Lorentz, when I wrote down these states, I didn't put the arrow on top of them. I was completely thinking relativistically. So they were classified by 4 vectors. Okay? Of course, these are 4 vectors that are on the mass shell, and this is what tells us that we're on the mass shell. Well, but we can go from here to here, and we did it by using these delta functions. We get something that looks like this. Evaluated at k0 equals, or supported on the, remembering that we are on the support of this delta function. Yes?
Can you remind us why you follow the cats as why the cats were invariant?
Why we thought about them as being, well, they are not Lorentz invariant, in fact. The cats themselves were not Lorentz invariant. Remember that when we apply Lorentz transformations, they change. Okay? But the way they will change will cancel each other because it's a unitary transformation. And therefore, this whole thing will be Lorentz invariant. Okay? But now if we want these 2 formulas to look the same, we have to redefine, or the connection would be that the relativistic case, which are nicely normalized, would be square root of omega k times the old case that we had before. Actually, there is a convention for the normalization, which I should actually do it. There is a factor of 2, and there is a 2 pi to the 3/2. Okay? And these are the one particle states that we had. Of course, if these guys are scalar particles as they are here, then they will be invariant, right? But if they represent other kind of particles with higher spins, then they will transform so as to keep this will still be Lorentz invariant, okay? But in this particular case, they are just Lorentz invariant because they are a scalar, okay? Of course, under a Lorentz transformation with lambda, this k will also change, okay? But the whole completeness relation will still be Lorentz invariant. Sorry? Yeah, that's what I tried to say, that if you apply a Lorentz transformation, we know how they will transform, right? They will go into lambda k. But this integral will still be Lorentz invariant because we're integrating over all k's. Okay? Very good. So let's finish today. I guess we have to finish. At what time? So we decided what, that we can finish at 5.
Well, we need
No, I'm fine. So I mean, I know you. You guys, yeah, you guys must be tired and.
So the last time you can get food from the beach was 7, so we can.
Okay, let's just finish by discussing a little bit of causality in the theory. So what are the observables in this theory? Well, the observables in quantum mechanics are any Hermitian operators, right, that you can write down. So those are in principle observables. But here, in quantum field theory, we also have an extra constraint, which is causality. So what does it mean? It means that if you have an observable O, we don't know what it is, but let's assume that we are looking for something that are called local observables. What we mean by that is that it's an observable that depends on a particular space-time point, a single space-time point. Okay, so we have different observables at each space-time point, okay, or different sets of observables. So that's what I mean by a local observable. Now, if this is an observable, if this operator is an observable, then, and say you have another one in the set, so we should give names, so this is a set. So if you have two operators, let's call them O1 at X, and you have another operator O2 at a different space-time point Y, okay? So what do you think is the requirement that our theory preserves causality? So imagine that we have the point X here. This is the light cone. Imagine that Y is somewhere here, okay? So if these two operators are observable, okay, it means that we should be able to diagonalize them simultaneously. It means that we can measure them simultaneously, right? Now, if for any reason these two operators, when we compute their commutator, and X and Y are space-like separated, in our metric, this means that X minus Y squared is less than 0. So what should the requirement be? That this should be 0. Every time this is true. Of course, if it wasn't 0, okay, then a measurement here could affect a measurement here, And therefore, we will have propagation of information at speeds faster than the speed of light. Of course, by Lorentz transformation, we could even go back to the past. So all these points are connected by Lorentz transformations, right? So this is the requirement that we should impose on the set of observables in our theory. Now, for our scalar field, what are the possible observables or the possible local observables? Well, we don't have much, right? We have just the field phi. So for our Klein-Gordon theory, what kind of observables can we imagine constructing? Well, we could imagine functions of phi. Okay. So is it true that the set of functions of phi satisfies this property? Yeah, so this time it would be a safe bet to say yes. And that's what we're going to do tomorrow. We're going to find out that this is indeed true. But if you want to, I mean, if you feel that you cannot sleep unless you know unless you see explicitly that this is actually true, then
This follows the communication. We just take the theory.
yes. So just try the following. If for any functions to satisfy this is enough to show that this happens. Okay? So you have all the tools you need to show that this is true. Yes?
Here we have the only information that I have is at equal times, right?
Yes.
So in this case, this is stronger, saying that I can have the commutation at different times, but just by preventing that it's space-like only. Okay.
That's right.
So I cannot use this as an argument saying that I can generalize my commutation relations and just work in space-like separation.
Well, you have to work it out. Somehow, you see, the canonical commutation that we did is something that doesn't treat the space and time in the same way, right? So there is no reason to believe that this object will be Lorentz invariant, for instance. So one has to work it out and see what happens. So hopefully, the object will be Lorentz invariant. And being Lorentz invariant, in other words, if you show that this object is Lorentz invariant, guess what you can do? You can find a Lorentz transformation so that this guy goes here. So it becomes at equal times with this guy. But then that's the condition we started with. So what you're going to do, basically, amounts to proving that we haven't done anything wrong with Lorentz transformations, which actually would be bad, right? So you're going to show the consistency of doing something violent to the system at the beginning, separating space and time, and then in the end getting something that magically goes back and restores the full Lorentz invariance. Okay? So I hope this is enough motivation for you to do it tonight, because you'll say, yeah, we cannot sleep unless we know how this happens, right? Okay, very good. I think this is a good point to stop.